What makes the difference between a great corporation and its competition is the expertise that it has. And the expertise that makes the difference is built up over years. And one of the goals of JMA is to get the brightest people we can possibly find worldwide. It really is worldwide now. We've just started up an operation in Australia, and the group of people that are coming together down there, like the people in this room, they're the most brilliant people that we can find in Australia. Now, talking to you last night, a lot of you were saying things which were pretty exciting. A lot of you have got knowledge in your heads which is special, but which really needs communicating to other people in JMA. And so therefore, as David was saying, one of the very important things that we've got to do now in running the business is learn how to capture that knowledge, which is in the heads of the brightest people here. Capture the knowledge, get it into a form in which other people can use it, and share it and learn how to apply it as effectively as possible. Now, we've reached a new point in time in the running of corporations like this. We can do something which Arthur Andersen's have never done, and the big 8 accounting firms have never done. And that is capture the brilliance that exists in the heads of a lot of you and get it into a computer. And organize it in a computer in a structured fashion so that we can get it onto the desks of other people. So I believe there's a new type of corporation that's going to emerge in the 1990s. There's a very good book that you might like to read called The Expert Corporation that was written about corporations that make a high level of use of expert systems and artificial intelligence and computers. And so in order to get the maximum use of expertise in a corporation, we need to capture the expertise from the individuals and then get that expertise into computers. And get it into a computer in such a form that other people can use it and find their way around it and put it to work as effectively as possible. Collective expertise can be optimized. It can be grown faster with a computer. It can be multiplied because we can get it to everybody's desk, and it can be protected with the use of expert systems. Now, in order to do that, we've been building a tool, and that tool is called MediaBrain. And MediaBrain, I think Ian is probably going to demonstrate it to you. And this is basically a hyperdocument tool. What we mean by a hyperdocument is that you have the document broken up into envelopes, and you can have envelopes within envelopes within envelopes. You can point to an item on the screen, and when you point to that item, it links you to a different envelope, which may appear in a different window or may occupy the whole screen. So a hyperdocument is a step beyond hypertext. And the envelopes in a hyperdocument might be text, like hypertext, or they might be pictures, but now we're moving into the era of the multimedia PC, which is not quite here yet, but it's pretty close. And as we get the multimedia PC, then the envelopes can be speech, or music, or television, or animation, and the envelopes can be computer programs. So the envelopes can contain segments of expert systems, or can contain spreadsheets, or can contain project management tools. We'd like to get project management tools where we can point at a bar on a PERT chart and it will hyperlink us into details of the methodology about what one does at that particular point on the PERT chart. So you might like to take a look during this weekend at MediaBrain, and we've built several different things with it. In fact, I think we've built some of the most complex hyperdocuments in the world. The IEM, Information Engineering Methodology, which Ian will talk about, that has been capturing the knowledge which we have about ISP and BAA and building that into a computer system so that people can use that on their desk to guide them in the methodology. One of the very important areas that we want to go in is very rapid application development. I'm particularly impressed by the work that Graham Fairley has done in London in using the IEF to create applications at a rate which averages something like 1,000 lines of COBOL per day, whereas the average world COBOL programmer is doing something like 20 lines of COBOL per day. Quite enormous difference. Now, there are various ways in which one can do very rapid development. And so we've been scouring the world for organizations that have succeeded in doing development that's much faster than anybody else and trying to find out how they've done it. Can we capture their expertise? And what we find is that different organizations, having done that, have done it in somewhat different ways. So can we capture the best of the different ones and synthesize that into a methodology which gives us the capability to build applications at very high speed, but extremely important, they must be applications of very high quality. So very high quality, rapid development. So there's a methodology for that, which is now being put into MediaBrain. So again, that methodology can be shared by all the various people that are using the IEF or using tools other than the IEF for very rapid development. Now, for a long time, I've been interested in future technology and spent a lot of time at seminars and things talking about where technology is going. And that's pretty exciting at the moment because the 1990s is going to change the world more than any other decade in history from the point of view of technology. There are more new things in the research labs now than there have ever been before, and some of them have quite awesome power. And so we would like to be able to understand the implications of that future technology. So for quite a long time, I've kept a future model, and the future model has a lot of different pieces of knowledge about technology, and all of these pieces of knowledge need to be linked together because one thing affects many other things. And so the model becomes a very complex model with lots of linkages in it. And MediaBrain was originally designed to handle that model of the future. And so therefore, there are three main thrusts in which JMA is heading. The main thrust and the major money thrust, and it will probably be the biggest money generator for the next 2 years or so, is information engineering, and particularly information engineering relating to the Texas Instruments IEF, but extremely important to our customers, very rapid application development. So we want to acquire the expertise across the company to build applications very fast and enable our customers to build applications very fast and make sure that those applications are extremely high quality applications. So we refer to that as RAD. My 14-year-old daughter tells me that RAD is an okay word to use, and rapid application development. It seems to be a word. I've been using it in seminars for the first time in the last 2 weeks. And when I talk in seminars for a day about the details of the techniques for the development of very high quality systems at very high speed, the audience almost always comes up on the stage. It's generating much more excitement than information engineering. And so we need to make sure that we have the capability to do that, and where we have customers which are information engineering, to make that an integral part of information engineering. And strategic planning, top management, really needs help these days. They are building computerized corporations and they don't understand it. They've got an extremely difficult job in trying to work out how you computerize a very complex corporation. And the new technology offers all sorts of new business opportunities. And if their competition seizes those new opportunities before they do, then they're likely to get badly damaged by that. And so therefore, we want to evolve JMA to the state where it's an excellent corporation in giving advice to top management about how to use computers and what are the strategic opportunities in business. And so that very much relates to the future model of technology. And so to start that, Core put together the 2020 study. The 2020 study uses the model of the future and attempts to use the model of the future so that we can look at specific corporations or specific industries. Look at banking and look at insurance and look at airlines and so on. And we now have slightly less than 50 joint studies which are going on with various corporations. And one of the things we're finding is we're learning an awful lot about other people's business. When one says, this is what the future of technology is going to do, and the future of technology is going to change your business strongly, and we then start to interact with the people who've got a sense of the future in a large bank or large insurance company and so on, we begin to jointly put together some fairly dramatic ideas about how banking is likely to change in the 1990s. Now, that's going to be a very, very interesting period over the next 5-6 months or so in JMA. But as that happens, it's very important that when we acquire that very interesting, very valuable knowledge, it shouldn't just reside in the head of the consultant that does it. We want to get it out of that consultant's head into a form where other people are going to be able to use it. So we need to be able to capture that extremely interesting knowledge that we find out, capture it, get it into a structured, computerized representation so that we can get it onto the desks of other people. So this is one of the things that MediaBrain has the goal of doing. Well, now let me spend some of this session talking about technology and where it's going so that you'll get an idea of what's likely to be happening in the 1990s. The 1990s is going to be a pretty exciting decade for people like yourselves who are interested in technology. I brought a portable computer over to Europe, which is the first computer in the world where the memory chips in it are 4 million bit chips. So now for the first time we're getting 4 megabit chips rolling off the production line. And the first computer to use those chips is the IBM Portable Model 70, which has the distinction of being the world's heaviest portable computer. In fact, I had a call from one of the express mail companies in my home in Vermont. And they said, we have a delivery for you, but we wondered if you'd mind if we deliver it tomorrow rather than today, because we want to put an extra person in the truck to carry it up to your house. And what he was talking about was the IBM personal portable computer. And now, well, one of the reasons why it's so heavy is that IBM designed that so that they can manufacture it more cheaply than South Korea. And in order to do that, they want to have a production line where there is very little human time. We obviously can't compete with South Korea in terms of people, because the people there are much cheaper than the people here. And so the IBM Portable Model 70 has been designed so the total amount of human time in assembling it, what would you guess? How many person days, how many person months would you think to assemble a computer like that? IBM says 15 minutes. So associated with that, there is the most dramatic example of a highly automated factory, and the whole computer has been designed so that the pieces can be assembled by robots, robotic fabrication line. And now clearly if we can do that with the portable Model 70, we can do it with television sets, and we can do it with vacuum cleaners, and we can do it with all of the other mass-produced goods that are part of society. So a major part of the 1990s is going to be the evolution to highly automated factories. And in order to evolve highly automated factories, we've got to redesign products fundamentally, redesign them so that they're capable of being fabricated by automated techniques. The key to a very high level of automation is to redesign the product so that it can be fabricated by the automatic machines. Now, the memory chips, the 4 megabit memory chips, are made in a plant which I think is the world's most advanced memory chip plant. It's sort of the popular conception that the most advanced chip plants are in Japan, but the Japanese aren't close to getting 4 megabit chips as yet. The 4 megabit chips come from a plant in the hills of Vermont, where most of the people around there are in the farming community, sort of beautiful area in Vermont. And this is one of the most esoteric factories you can imagine. And that factory is now, they are now building their new factory to make 16 megabit chips. And the 16 megabit chips are going to be rolling off the production line there in 1992. In order to make 16 megabit chips, we've got to make the components extremely tiny indeed. And indeed, the components on the 4 meg chip are very tiny. One of the fascinating things about the 4 megabit chip is it's exactly the same size as the 1 megabit chip, just actually slightly larger, approximately the same size. And it takes the same power as the 1 megabit chip. Both of them take half a watt. If the amount of power increased with the number of bits, then as you built up to large memory, you get heavy overheating in chips of the future. So those things are important. Now, in 1992, they're going to be making 16 megabit chips. In 1995, they tell me they're going to be making 64 megabit chips. In 1998, they're going to be making chips with 250 million bits on them. And the scientists are fairly confident that they know how to push up to 250 million bits. It's likely that 3 years after that, they'll be making the world's first gigabit chips with 1 billion bits of memory. But there are lots of very severe technical problems that the scientists don't quite know yet whether they'll be able to solve in order to push up to billion-bit chips. Now, at the same time, Intel makes the processor that's in that computer. And we're now beginning to get the Intel 80486 processor coming to the marketplace. The PCs we've got lying around the building today have either got Intel 286 or Intel 386 processors in, and the 486 is more powerful than a mainframe, one little chip, which is more powerful than a mainframe was in 1980. And Intel say that they'll have, in 1992, the Intel 586 chip, which will become a 100 megahertz chip with 4 million transistors. In 1995, the Intel 80686 chip, which will be 150 megahertz with 22 million transistors. And in possibly 1998, the 786 chip, which will be a 250 megahertz chip. Well, now, while we're getting those chips from Intel, there will be other processor manufacturers in the computer industry that would say, who needs them? Because we have a faster way of doing computing now, and that is with RISC chips. So in the 1990s, there's going to be a big battle between the chips which are like the ones in the IBM PCs today and fundamentally different chips which are RISC architecture chips. The idea of a RISC architecture chip is that you eliminate all complex instructions, you eliminate all slow instructions, and you optimize the design of the chip for maximum speed at the expense of the software. And that means that you've got to have very sophisticated compilers and interpreters to create the software for the RISC chip. But the RISC chip vendors are saying that by 1990 they'll have a 25 MIPS chip, by 1993 a 100 MIPS chip, by 1995 a 250 MIPS, million instructions per second chip, and by 1998 they'll break the barrier of about 1 billion instructions per second on a RISC architecture chip. So this is the way that the raw technology is changing. Well, now what we'd like to do in the model of the future is to get as much of that information as we can, put into a computer, and find out why it's happening. We'd like to plot curves which show the trends. Those are the trends for memory chips there. In order to really understand this, we need to understand why. Why are the chips getting faster? Why are we capable of doing things better than that? The reason we're capable of doing it is because the components are getting much smaller, but as they get much smaller, we can't etch them with light anymore because a photon is too large. And so we've got to move to something that's a smaller wavelength than light. So what's happening over the next 6 years is we're moving through the ultraviolet spectrum to use radiation of higher and higher frequency, smaller and smaller wavelength to etch the chips of the future. But by the time we get up to the 250 million bit chip, we've run out of the capability to do that. We can't go any further through the ultraviolet spectrum, and so therefore there's got to be a fundamental change. There's been an argument in the IBM plant about whether this change will be necessary for the 64 meg chip, and they think not. They think they'll be able to make the 64 meg chip with conventional techniques, but by the time they get to the 250 million bit chip, they will have to use nuclear technology. And so they have a device like this, which is a synchrotron, and a particle beam races around there at extremely high speed. And when we take a very high-speed nuclear particle beam and bend it with a magnet, it emits radiation. So what we do here is use a superconductivity magnet to bend it very sharply, and it then emits X-rays, and the X-rays are taken into a workstation and focused, and it's that X-ray beam that will be used for etching the chip of the future. Now, the cost of a factory using something like that is extremely expensive indeed. As we push forward the frontiers of technology, so the cost of one single chip factory becomes absolutely enormous. There's in an African country a replica of the Vatican that has been built. I don't know whether you've seen its pictures in the magazines. It's like the design for St. Peter's, done by Leonardo da Vinci. And it's got the courtyard there, it's got St. Peter's. It's actually bigger than St. Peter's, and it's replicated the pillars and the architecture and everything. The thing which I find quite extraordinary is that that absolutely spectacular, magnificent replica of St. Peter's there costs substantially less than one factory for making memory chips today. That's how expensive the memory chip facilities are getting. So it's becoming very big business. Now, in order to push forward, we've got to make things much smaller, and so here's an electron microscope photograph showing a transistor where the diameter across there is 1/10 of the diameter of the transistors you've got in your PC today. The diameter across there is about 1,000th of the diameter of a human hair. It's 1/10 of a micron. The computers we have today have dimensions of 1 micron. And by about 1996, we'll have pushed down to about 1/10 of a micron, and we have built 1/10 of a micron circuits in the laboratories, and we now have to get them from the laboratories into billion-dollar factories which can mass produce them, and that's a difficult thing to do. Now, there's been one quite extraordinary invention in the last few years, and that is a new type of microscope. That picture there was taken with an electron microscope. And an electron microscope is a huge $1 million instrument filling a whole room which can photograph very tiny things, much tinier than an optical microscope. But there's been an extraordinary invention to create a new microscope, which is so small you could hold it in the hand, and this can photograph things much tinier than can be photographed with an electron microscope. In fact, here's a photograph which almost no scientist would have believed possible 5 years ago. This is a photograph of a gallium arsenide molecule, gallium arsenide being very important in microelectronics, and it's a photograph which shows the actual atoms on gallium arsenide. Now, no scientist would have believed it would be possible to take a photograph which shows the actual atoms in a molecule. And that has been done with this device here. And the way it works is there's an extremely fine probe on this device which sends a current to the surface that it's photographing, and then you move this very, very slowly. And as you move it, there are changes in current, very minute changes in current, and you pick up those minute changes in current and feed them into a supercomputer, and with very high-speed processing, the supercomputer puts that information together and then later compiles a picture which is a photograph of the surface. Now, in Bell Labs, they've gone a step further. They've been able to take this device here and not only photograph atoms, but deposit atoms. And as we get the capability to deposit atoms, then that gives us the ability to do engineering at the molecular level as opposed to very large engineering. The transistor which you've got in computers today and the wires which you've got in computers today are about 10,000 atoms wide. And so there's a lot of progress we can make in shrinking those to being about 100 atoms wide, and then pushing them down to much smaller than that. And the scientists are saying that we can probably get down to about 1/100th of a micron, but it's going to take a long time to get there. A lot of knowledge and a lot of new techniques to be able to get there. Anyway, what we'd like to do is to be able to put all of those facts together and say, what's the meaning of this? What is it going to do to the world as we get that technology? And so therefore, the model that we have of the future in JMA looks like this. The basis of the model, the bottom layer of the model here, is the core technology, which is chips, what's going to happen to chips, what's going to happen to optical fibers, and so on. And as we get more powerful chips and more optical fibers, that means we can build better machines. So we can start to say, what is the PC going to look like at various different eras in the future? One of the extraordinary things about asking that question about the PC is there's not any serious doubt that at a certain point in time in the future, the machine on your desk is going to get more powerful than the most powerful supercomputers in the world today. And that raises an interesting question. What the hell do you do with it? Now, if you've got that amount of power on the desk, what are the applications that we would use it for? And clearly there are some applications which are quite different from the applications of today. There's some applications which are generic applications. So if we can identify what are the machines going to look like, what are the systems going to look like, then we can start to say, what are the generic applications which don't apply to any one, apply to all industries rather than one specific industry. And some of the applications that are going to be very important are intelligent documents, documents that have got expertise built into the document itself. When a Chrysler M1 tank goes into battle, for each 4 M1 tanks, there has to be an armored personnel carrier full of paper for them to maintain all of the things on the tank. And that really doesn't make sense. What we'd like instead is to have a compact disk in the tank where the compact disk has got all of that knowledge, and on the same compact disk there are expert systems which tell the maintenance technicians how to do the maintenance on the tank. So intelligent documents are going to be very important. Intercorporate networks, we're now beginning, in most of the past world of networking, we built corporate networks built with SNA and DECnet. We're now beginning to build intercorporate networks. And there are quite a lot of spectacular examples of intercorporate networks, and we find there's a high profit associated with the generic applications of intercorporate networks. For example, we can reduce inventory. We can do things much faster. Just-in-time inventory control. The computer in a manufacturing corporation is going to be online to the computers in its customer corporations, and online to the computers in its supplier corporations. So the world's going to look very different by 1995. Instead of having mailmen trudging through the streets and computers printing out masses of paper, We're going to get rid of all of that paper, which will mean that we do less damage to the ecology of the planet. And instead, over optical fibers, we'll be transmitting signals. And instead of the paperwork having to be key punched by people into computers at the other end, that information from one computer will go directly into another computer. So the world will become a world where the computers are laced together into networks, into corporate networks. The computer in one corporation automatically transmitting information to computers in 1,000 other corporations. And that's really going to be a very different world in many ways. Anyway, having identified generic applications, we then work in the banking sector, and so we've got various banks that are working with us in the airline sector and the manufacturing sector and the entertainment sector, broadcasting, and try and work with companies like that and say, what is this new technology going to mean for those organizations? And as we put all of that together, there's no question that banking is going to change in some pretty traumatic ways in the 1990s. So we would like to be able to understand that as well as we possibly can, so that we can then talk to top bankers and tell them our views and why we have those views, so help them to do strategic planning of how they would use computers in the organization. But as all of these changes happen, so they're going to make a lot of changes to society. And so therefore we need to be asking the question of how is society going to change as we get into corporate networks and as we get very powerful chips and change industry and so on. So very, very big and very powerful changes that are happening. Today's wafers, where we make chips, are 8 inches across in the most advanced factories. Many factories are about 5 inches across. And so we take masks of what we want to be on the chip, and we build up layers of chemicals to produce a surface there, which becomes a microcomputer or a memory chip, and so on. And what's likely to happen as we evolve from this point on is we're going to be able to make the components on there very much smaller so that we can get more on one chip. And so that's what most companies are driving for in microelectronics today. But there's something immensely more powerful than that, and that is that if instead of making it a two-dimensional chip, we could make it three-dimensional, then you're going to be able to put much more on the surface of the chip, and you're going to be able to have much shorter distances. Much shorter distances mean much higher speeds of interconnecting components. So a lot of the research now is trying to work out what are the implications of having three-dimensional chips as opposed to chips on one surface. And scientists are saying they think they're going to be able to build factories which can put about 100 layers of microelectronics onto one chip. And incidentally, that is not, I was saying that IBM is going to make 64 meg RAMs and then quarter gigabit RAMs at the dates we mentioned. And those are going to be conventional. Those are going to be conventional electronics, which are two-dimensional chips. Now, as we make three-dimensional chips, then we can build things of much greater power and much greater speed, but there's a very severe heat penalty in doing it. The heat penalty is such that if you for example, access a memory bit here, then you've got to make sure that you don't access the same area again for a certain amount of time, like 50 nanoseconds or something like that. And so therefore, that means that we've got to put constraints on how we use microelectronics like that, which are in turn going to fundamentally change the operating systems at the lowest level. Now, we can build many chips onto one substrate. And so we have modules like that. That is 3 inches across. That's one of the thermal conduction module units. We refer to this as multi-layer ceramic unit, which goes into the IBM mainframe. And the thing gets very hot, and so in the IBM mainframe, a major part of this technology is the cooling. And so here is the thing which draws heat away. There's the chips. Here's the 3-inch block that we have there. Now, one of the reasons why that gets very hot is because it's built with bipolar technology. And CMOS technology doesn't get hot like bipolar technology. So therefore, one of the challenges now is to say, let's get that out of bipolar technology into CMOS technology. Let's design it so that we can build a sandwich in which we have many layers, and at the latest level, this has got a 43-layer sandwich. Each layer there has got a densely printed circuit on it. There are laser holes drilled through it, and the red things are the individual chips there. Now, if we get that to CMOS as opposed to bipolar, then we can get it into a personal computer. And so this gives us the capability to put a quite enormous amount of logic or an enormous amount of memory into a personal computer. And if we can then start to do that, then we can begin to ask the question, how can we make this as fast as possible? Well, we'd like to make those chips as powerful as they possibly can be, so move them up to 16 meg RAMs, 64 meg RAMs, and so on, where these are microprocessors, make the microprocessors as fast as possible, so RISC architecture microprocessors of maximum speed. And now, today, on the ceramic here, these wires are electrical wires, and electrons move rather slowly in wires. Some people think that electrons move at the speed of light. They don't move at anything like the speed of light. They move about 3,000 times more slowly than light. But if these wires, instead of being electrical wires, were optical wires, then the photons would move at the speed of light. And so therefore, we'd like to say, can we take electrons on a chip like that and convert them into photons and then use optical wires on the substrate? Because if we could, we can increase the speed of this by a factor of 1,000. And so this is one of the big arguments that's going on. At the moment, it's quite expensive to convert electrons into photons. And so the conversion process puts a cost limit on it. Today, with the technology we have today, any wire in a computer which is longer than 1 meter, it's economic to make it an optical wire rather than an electrical wire. And that distance of 1 meter is going to steadily shrink and shrink and shrink as we go through the future until it drops down to more like a centimeter than a meter. Now, as we do that, we then get the capability to put many computers onto one substrate or many computers onto one single chip. So as the chips become very dense, instead of having just one processor, we may want multiple processors. And as time goes by, the number of processors will grow and grow and grow until by the time we get to the era where we're talking about gigabit chips, we are going to have thousands of processors on one single chip, ultra-parallel computing chips. That's got enormous software implications. How do you write programs for ultra-parallel computers? We have some examples of ultra-parallel computers. The connection machine today has got 64,000 processors in it and very different software, and it can do very different things. But these are some of the things which are likely to change computing. And as we change computing, it's clear that we're moving to some fundamentally different types of computing. Computing is going to head in very different new directions. Ultra-parallel machines, inference engines which can do automatic reasoning in artificial intelligence, programming by case tools. The key to a very high level of parallelism is very advanced case tools so that the programmer doesn't have to think about what activities go on simultaneously. That can be worked out for him automatically by computerized tools. AI computing, ultra-parallel knowledge bases. And now, even if we built the most powerful parallel computers and the most powerful supercomputers with today's technology, they still don't get anywhere close to the human brain. With the human brain, you can do things we can't possibly imitate by programming in any way whatsoever. For example, you could be walking down the street and you could see somebody 2 blocks away and recognize their face. You could see somebody you haven't seen for 20 years and recognize their face 2 blocks away. Now, how do you do that? We couldn't possibly program a Cray 2 to do that. The world's most powerful supercomputers couldn't do it. So it's very important to understand the human brain is quite unique, and it would be a total misconception to think that the very fast computers we can build in the future are going to replace the human brain. The human brain can do all sorts of things that computers will never be able to do. But biologists have got very interested in the mechanisms of the human brain over the last 10 years or so. So there's been a lot of research into how the human brain works. And your brain is composed of neurons, and we know pretty much exactly how a neuron works. We've separated neurons. They've actually, in Bell Labs, taken neurons and connected them up to electronic circuits so that you can have a neuron wired into a chip. So we know how neurons work, and we can electrically produce analogs of neurons which do exactly the same thing. So if we can produce something that's electrically exactly like the neuron in your human brain, why can't we build something like the human brain? Well, the human brain has got one fundamental difference to a computer. In a computer, a logic gate is connected typically to 2 or 3 or 4 other logic gates. In your brain, one neuron may be connected to 10,000 other neurons. So the human brain is something which has got an absolutely massive degree of parallelism in it. And so the people with silicon are saying, well, if you can have massive parallelism like that in the human brain, surely we can build massive parallel into electronic circuits. And we refer to that as neural nets. So one of the technologies that there's been a lot of excitement about over the last 5 years is neural networks. Much of that started in universities and went on in universities. And it began to work reasonably well. What we mean by a neural network is that you build a silicon version of a neuron, and the neuron has got various inputs going into it, and we build up these neurons into patterns like that. There are many patterns that we can create, so many possible types of neural network, and there's a lot of mathematics that goes on to try and work out what are the best patterns of neurons that will work in the most effective way. And we can clearly build silicon circuits which have got extremely large numbers of neurons indeed, and today there's not much difficulty in getting up to about 10,000 to 100,000 neurons. The most advanced neurocomputer in the world has got 1 million neurons, and 1 million neurons is about the same as a housefly. A housefly has got about 1 million neurons in its brain. You've got something like 10 to the 11th neurons, but only about 10 to the 10th of those relate to the thinking part of your brain. Your cerebral cortex, where you store all of your memories and do all of your thinking, that has got about 10 to the 10th neurons, which doesn't sound a terribly large number by today's computing standards. And so I was trying to explain to Ian Palmer that his brain power was the brain power of 100,000 houseflies, but he didn't seem to appreciate that too much. Anyway, we now have boards like this, which we can put into a personal computer, which are the world's first practical neurocomputer boards. And the neurocomputer can do things which we can't do with supercomputers. It's exceptionally good at pattern recognition. It's exceptionally good at learning circuits. And over the next few years, that neurocomputer is going to get much faster. And there's not much doubt that by the time we get up to the year 2000, we can have extremely high-speed neurocomputers. Now, at the same time, telecommunications is evolving very rapidly. Here's an optical fiber that dates to about 1980. This is a telecommunications optical fiber. And the signal transmits over these little hairs of glass. And that optical fiber, the state of the art in that technology in 1980 was that it could transmit 45 million bits per second. In 1982, it could transmit 90 million bits per second, and the year after, about 180 million bits per second. By 1986, 565 million bits per second. Today, LM Ericsson are making optical fibers which can transmit slightly more than 1 billion bits per second, and in Bell Labs, they've got optical fibers which transmit at 16 billion bits per second. So the rate of change of optical fiber technology is much faster than the rate of change of computer technology, even though the rate of change of computer technology is so enormous. And the physicists know what they have to do in order to make optical fibers much faster as we go through the 1990s. And the measure of effectiveness in an optical fiber is the distance multiplied by bits per second. And so that is the measure of goodness, if you will, in optical fibers. And what they're saying is that they can double that number every year for the next few years, probably for the next 10 years, though it's going to slow down a little bit as we get towards the year 2000. And so what we're trying to do in the 2020 study is put together all of these facts, see how they fit together, and then try to work out how are these things going to change in the future. So the model that we have then has the core technology, the machine technology, the applications technology, and the impact on society. And we projected that about 30 years into the future to the year 2020. And by now this has become a massive body of knowledge in a personal computer. And now, as we go through the current 2020 study with the current customers, it's very important that we capture that knowledge and grow the model and then work out what are we going to do with that next year. And what are we going to do with it the year after that? So we want to convert this knowledge and package it so that eventually it becomes a resource which will enable us to give advice to top management. And so we use the term enterprise engineering. What we really mean by enterprise engineering is you've got to look at the enterprise as a whole, say how can that enterprise change because technology is changing so rapidly? What are the opportunities for the enterprise to change in the way which will give it the maximum return on investment? What are the ways that it can use technology to gain a major strategic advantage over its competition? Now, as we identify those ways, we need then to say, okay, now what sort of computing resources do they need? So we need to do information engineering across the corporation. We need to do architecture planning so that we have connectivity and portability across the enterprise, and that's really quite different from information engineering. And we then need to be able to drive down to the bottom and be able to build applications. Some of the applications we refer to as strategic applications, and one of the characteristics of strategic applications is the corporation that gets there first wins a major advantage over its competition. So as we identify the strategic applications, so we must be able to build those fast, and so therefore we need RAD technology, rapid application development. So you can see how these things fit together. At the top, a concept of the future, which leads to strategic planning feeding enterprise engineering, information engineering, that identifying the most important, the most strategic applications, and then the capability to build the most strategic applications fast with rapid application development. Now, the goal in JMA now is to say we want to become excellent in all of those things. We want to be able to do all of those things much better than Arthur Andersen, or the Big Eight can do all of those things. And the Big Eight tend to be run by people who are bureaucratic. The one thing which we must absolutely prevent in JMA is bureaucracy setting in, so that we take a bureaucratic approach to methodologies as opposed to constantly changing methodologies to use the most powerful new techniques that we possibly can. And the people in this room are absolutely capable of doing that. It's very important that we go on hiring people like yourselves, the brightest people that we can find in the industry. But as people like yourselves get great ideas, and you're all getting great ideas, we've got to capture that knowledge, capture the knowledge and structure it, get it into a form where we can share it by using a computer. And if we do that, we're then going to build up a completely different type of consulting corporation from any corporation that the world has known so far. Let's break for coffee.